Hi, everybody. This is Miss Wiesen, and today we are going to start the fifth unit in AP Chemistry. And this is, for many of you, probably going to be relatively new information, or if you had it in honors chemistry, you probably had just the basics. And this is going to be over something called chemical kinetics. And that's just fancy terminology for the rate in which a reaction occurs. So, how quickly a chemical reaction occurs. We're also going to take a look at something called rate mechanisms, and we will, of course, talk about this throughout the entire unit. Let's title our notes Unit 5. We're obviously going to keep a hold of these until the very end of the year, so we have them as a reference point. You might also want to pull out some extra paper to take notes on. You want your AP reference sheet, a writing utensil, and yes, this is the unit we are going to fire up those calculators and actually do some graphing. We're not going to do it in today's podcast, which is going to basically cover factors that affect rates of reaction, but we will certainly be using those calculators and offering some tutorials on how to do graphing here in a couple of podcasts coming up. So what is chemical kinetics? Chemical kinetics is the study of the speed or rate of a reaction that is occurring under various or certain conditions. Now, one of the connections here that you might be aware of is when we say speed or rate, most of you that drive know that in order to determine how fast you are going to look at your speedometer, and it tells you how many miles you are going per hour. Now, in other countries, it might be kilometers per hour, but here in America, we use miles. And so, generally speaking, when we are talking about a rate, when we're driving our vehicles or how fast we're going, we're talking about a derived concept of change in distance we're traveling over an interval of time, right? And so, what we're going to look at in this unit is the speed or the rate at which chemical reactions occur on the molecular level. Now, before we start talking about the factors or the things that affect how quickly a reaction occurs, I want you to know that in order for a chemical reaction to occur, it has to be what we call thermodynamically favorable. All right. So make a note that just because a reaction is thermodynamically favorable, it does not necessarily mean or imply that the rate of that reaction is fast or rapid. I mean, if you think about it, think about the formation of diamonds. That's a thermodynamically favorable reaction, but it is a reaction that occurs so slow that it's not even detectable in a lifetime. And the reason is because certain reactions will have enormous or very large activation energies that must be overcome before the reaction can actually proceed. And then, of course, there's also reactions that occur very quickly, at which point they would have very small activation energies that they need to overcome for them to proceed. So, in this unit, I want you to dust off your algebraic skills because we're going to be using them a little bit later on. And again, we're going to fire up that calculator. So make sure you do have a graphing calculator handy for every podcast this unit. Now, this particular podcast is going to be more conceptual, and we're going to talk today about the factors that affect rates of reactions. And before we begin, I need you to be clear that when we talk about a chemical reaction, we are starting with the starting materials, which we call reactants. And then after some time passes, we will then have the formation of products. Now, I give you that as a reference point because I just want you to be familiar with the language you'll hear. Now, the first thing we have to consider about factors that affect reaction rates is something we call the nature of reactants. Now, this seems pretty obscure and vague, but let me explain what the nature of a reactant means. So some reactant molecules are going to react very quickly, while others are not. They're going to react very slowly. And that is because the phase of matter or the state of matter is actually going to come into play here. For example, solids are going to react much more slowly than liquids or even substances in their solution form. Physical state matters a great deal. Consider liquid gasoline versus gaseous gasoline. You're going to have, if you compare the density of the molecules in its liquid state versus a gaseous state, In that gaseous state, you're going to have less dense molecules. They're going to have more space and more freedom to move around. And then if you look at the example given below, I have two reactants here, two salts, and they're both in their solid state. And you can see here that no reaction occurs. Those two solids are basically just sitting next to each other, hanging out. Nothing's going on here. Whereas if these two solid salts were dissolved into water in an aqueous solution, then the ions of these salts would be more readily, they would be moving around, there would be more energy associated with them, there would be more collisions, and those collisions would give rise to potential opportunities for a chemical reaction. So again, usually the rule of thumb is that solids are not going to react as quickly as liquids, and liquids will not react as quickly as gases. That's the general rule of thumb. The other bullet point here under the nature of reactants is something we call chemical identity. And so if you're thinking, what does that mean? This is basically when you're trying to consider what exactly is reacting in this reaction. So for example, usually ions of opposite charges are going to react very rapidly. Also, the more bonds between reacting atoms in a molecule, the slower that reaction rate is. And that should make sense because more energy is needed to go into breaking those bonds before reformation of products can form. So more energy is required to separate those molecules into their bits, if you will. Also, substances that have stronger bonds, we also say larger bond energies, they're going to react much more slowly. An example would be taking metallic sodium and how that would actually react much faster in water than metallic calcium. Okay. Now, generally speaking, chemical identity, you can almost think of it as the size of the molecule. Okay. Generally speaking, the larger the molecule, right, the longer it's going to take for it to break down and react. Okay. So chemical identity and states of matter are two concepts that we would call and put under the category of nature of reactants. The second thing that affects the rate of a reaction, and you can see that listed here in your notes, is the concentration of the reactants. So how much of each of the reactants are you starting with? And so you guys have already learned in the previous units that we measure in chemistry, we measure concentration using molarity, big M, which is moles of the solute over liters of the solution. Don't also forget that we will oftentimes use brackets to represent concentration. I say that because you'll still see it in this unit, and you just need to be familiar with the terminologies and the shorthand notation. So obviously, it makes sense that the more molecules you have present, the more collision that those reactants will have, and the faster the reaction will proceed. Therefore, if you increase the concentration of the reactants, generally speaking, you're going to have a greater rate. Think of the passing period at Eagle Crest High School in the hallways and how crowded it gets, right? Compared to what it's like when everybody's in class, right? The higher the concentration of students, people are bumping into each other a lot more often and frequently. The third factor that affects the rate of a reaction is the temperature, right? The general rule of thumb, and we like to say this a lot, hey, if you heat them up, you're going to speed them up. And conceptually, hopefully that makes sense, right? If you heat something up, which is directly related to its kinetic energy, remember that is moving energy, the molecules are going to move faster. And the more likely that they're going to collide with other reactants. And when they collide, you'll see the energetic collision occurring. In other words, it's more likely to cause molecular damage, right? We speed them up, more molecular damage is likely to occur. Bonds are going to break, new bonds are going to reform, and so temperature can definitely increase the rate of a reaction. A couple more bullet points I wanted to add here is that an increase in temperature produces something we call a successful collision, okay? Now, this is important because in AP chemistry, when you're answering questions, you need to be able to speak the language of chemistry. So successful collisions is something I want you to add to your vocabulary. Sometimes you'll actually hear me call successful collisions effective collisions. So I want you to also write that in your note. And incorporate it into your vocabulary. Just do it, please. Okay, so if you increase the temperature, you're going to increase the likelihood of successful collisions that are able to overcome the needed activation energy. Okay, so all reactions take a certain amount of energy to overcome in order for the reaction to proceed. So if we increase temperature, those effective collisions, the molecules are moving around much more quickly, increasing effective collisions, therefore overcoming the needed activation energy needed for the reaction to occur. And the general rule of thumb, this is something they'll expect that you know, and so will I, that for every 10 degrees Celsius that you increase a chemical reaction, you can assume that it will actually double the rate in which the reaction is occurring. So this actually is going to depend on the magnitude. Remember, magnitude, swanky word for size. So this is going to depend on the size of the activation energy. And there is that word again. You guys keep seeing that this word activation energy keeps popping up. It's very important. In fact, I just highlighted here that we oftentimes abbreviate activation energy, capital EA, okay, E sub A. All right, so we're going to come back to talking about activation energy in more detail, but for now, keep that in the back of your head. We keep bringing it up. The fourth factor that affects the rate of a reaction is the surface area of those reactants. And this is generally defined as the exposed surfaces of the reactants that are available in the reaction. And so if you actually increase the surface area of the particles that are reacting, you're going to increase the chances of successful collisions between those particles, and therefore the reaction rate can proceed much faster. One of the things that you might vaguely hear about is the dangers of coal mines or even grain silos, and how actually they're very explosive. And so the example I put in our notes here is if you look at coal dust, like in a coal mine, for example, highly explosive. And that's because that aerosolized coal dust is in providing and increasing surface areas for it to react with the atmospheric air and oxygen. And you guys know that for an explosion to occur, we need oxygen. And so the fine dust particles of coal can interact with the oxygen molecules in the air and actually become very, very explosive. Now, you would not see that happen if you just had a chunk of charcoal that you set there. You can keep that out all day and nothing would happen. So anyway, surface area will, in fact, increase the rate of a reaction. Okay, they like to trick you on this one. There's a classic ruse here when they ask questions in the AP test. They're going to ask, what would adding a gas do to affect the rate of a reaction? And I'm going to tell you right now that when you add an inert gas, okay, it's going to have absolutely no effect on the rate. Okay. And then you might be thinking to yourself, well, why do I care? Well, oftentimes we do incorporate inert gases into chemical reactions as needed in part of the reaction mechanism. Okay. But overall, inert gases will have no effect on the rate. And if you're wondering what inert means, it just simply means non-reactive. Okay. And the number one column on the periodic table that you should draw your attention to in terms of non-reactive is your noble gases. So if you look at helium, neon gas, argon gas, those gases are not going to have any effect in your chemical reaction. Okay, the last factor affecting the rates of the reaction, and you've probably heard of this before if you've taken AP biology, is the effect of a reaction rate when you add a catalyst. Okay, and again, there will be lots of multiple choice questions that lurk on the test regarding catalysts. So we're going to talk more about this at the end of the unit, but for now, let's just do a quick overview. When you add a catalyst to a chemical reaction, it is indeed going to increase the rate of the reaction. However, you must also make a note, and I'm going to keep saying this, a catalyst is not consumed in the reaction. Okay, so when you add it to a particular reaction, when you add a catalyst to a particular reaction, it can actually be used again and again. So it's not consumed by the reaction in itself. And ultimately, when a chemical reaction does occur, that catalyst actually may participate in several of the chemical transformations that are occurring in any particular reaction. A catalyst is a substance that changes the rate of the reaction by, more specifically, altering what we call the reaction pathway. And we're going to talk a little bit more about what reaction pathways are, but really quickly, as an overview, most reactions don't occur in one fell swoop. They occur in a series of steps that we call a reaction pathway. So most catalysts are going to work by effectively lowering, and there it is again, the activation energy that is needed for a particular reaction to proceed. And therefore, the collisions are going to be successful, and then the rate of the reaction is going to be increased. One more time, remember, a catalyst is not part of the chemical reaction, and therefore it is not used up during the reaction. And lastly, I thought I should add this here because you might see it on the test. Catalysts can be what we call homogeneous or heterogeneous. And so if you kind of just break the word down, it is what it sounds like. Homogeneous means the same state as the reactants. So if you're using a homogeneous catalyst, it's going to be in the same state of matter as the reactants you're using in that reaction. And again, you could probably take a guess what a heterogeneous catalyst means. Hetero means different. So a heterogeneous catalyst is going to be in a different phase from the reactants that you're using. And that heterogeneous catalysts, they're oftentimes more stable, and they're actually more readily to separate from the reaction because they are, in fact, in a different phase as the reactants. All right, so what we just covered were the general factors that affect the rate of the reaction. Now, you have been hearing me say a lot in the last, 20 minutes or so I've been talking, is these successful collisions or these effective collisions. And that's when we need to talk about something called collision theory. Okay, so I want you to take a look at this graphic here, put me on pause, and see if it makes any sense. If you want to, you can just kind of refer to this as the first, this is being the second, and this will be the third portion of the graphic. Now, the collision theory states that when suitable particles of the reactant hit with each other, only a certain percentage of those collisions are actually going to cause any noticeable or significant chemical change. In other words, what I'm trying to tell you is that when you take reactants and put them together, it actually takes quite a bit for a chemical reaction to occur. The collisions that occur, they need to be successful collisions, okay? So when you have successful collisions, what that means is you're going to have the reactants colliding with enough energy, which we, again, there it is for like the fifth time, which is called activation energy, okay? So they're going to collide with enough activation energy where at the moment of impact between those two reactants, the Coulombic attractions between the two bonded atoms and the shared electrons is actually going to be overcome. And therefore, the bonds, the pre-existing bonds that hold them together are now going to break and new bonds are going to form. So this is going to result in products. When you have existing bonds breaking and reforming new bonds with other items, those are going to be your products. So increasing the concentration of a reactant particle or raising the temperature or bringing in a catalyst or increasing the surface area, all that stuff can actually bring about more of these successful collisions and therefore increase the rate of a reaction. If you look at the image that's given to you here at the bottom of page 2, go ahead and take a look at the first scenario. We have two reactants, and it looks like, just according to the image, and I'm hoping that you can tell, I think this is NO3, and then this molecule I think is CO. So it looks like we have NO3 and carbon monoxide coming together, but the reactants are moving too slowly. And so what you can see here after the arrow is nothing has changed. No reaction has occurred because since the reactants were moving too slowly, they just kind of bounce off of each other and, well, no chemistry. If you look at the second scenario in the image, you can see that when we have the two reactants and they're not oriented or facing the proper way, Again, after the arrow, you can see, again, nothing has happened here. They just, again, kind of bounce off of each other and no reaction occurs. But take a look at the third scenario, and this is actually what you need for a chemical reaction to occur. You need to have enough energy in the reactants, and they need to be oriented correctly. And when you have those two things happen, voila, you have the magic of chemistry. And so if you take a look, the products of that very last one now are NO2 plus CO2, which clearly are different from what we began with. So let's go ahead and move over to the top part of page 3. And I think we're going to finish up with this page, and that would be the end of this first podcast here. So again, very conceptual things, not necessarily hard, but fundamental to understand and know before we move on to more complex concepts involving chemical kinetics. Now let's take a look at what we just learned about that collision theory in the previous page. There are some essential components that you need to know to give you more of a comprehensive understanding of this theory. And that is, number one, particles, you guys, they got to collide. They have to. And second, most often, only two particles may collide at one time. Again, as it leads into the third point here, with proper orientation. Okay. And once that happens, you get this contact with each other, and hopefully we would get some products forming. Now, the fourth point of collision theory, which is over here, I'm circling it right now in case I kind of put some images there and chopped it up a bit. I apologize. But the collisions must occur with enough energy, I keep saying this, to overcome the electron-electron repulsion of the valence shell electrons of either reacting species. Again, that's going back to Coulomb's law, you guys. And they must have enough energy to transform what we call that translational energy into vibrational energy in order to penetrate each other so that the electrons can actually, in fact, rearrange themselves to form a new bond. And remember, we learned about bonds, metals and nonmetals versus non-metal only, right? Ionic versus covalent molecules. And of course, we also have metallic bonds. So again, when this happens, we are speaking of these collisions as being effective collisions or successful collisions, okay? Now let's take a look up here at this image. And what you're looking at here is reactant A and reactant B are coming at each other, hence the arrows pointing at inwards towards each other. And if the collision is a proper collision, what you will effectively have is the formation of new bonds to create a new product. Okay. Conversely, if you look at the image below, you will see that it looks like here the reactants A and B, A looks a little, they're not oriented correctly. And so what happens is you have what we'd call an improper collision. And again, the two molecules, they might come in close proximity to each other, but ultimately at the end of the day, no bonds are breaking and certainly no new bonds are reforming to form the new products. Therefore, no reaction occurs. Now, this image here on the left, this reaction diagram, this reaction progress diagram, okay, is very important. It's not going to be the last time you see this. You would, in fact, read it from left to right as you would a chemical reaction. And so over here, you're starting off with your reactants. And if you go all the way over to the right, you'll see that at the end of the day, we're hoping to arrive at the products of our reaction. Now, what's happening in between in terms of energy? Well, this potential energy diagram of the reaction progress of this example that we have here in our notes, what we're noticing is that if we have several of these reactants, they have to overcome an activation energy before we can start to see any kind of bond breaking between the original reactants. Now, once those reactants do in fact overcome and reach that energy level to start breaking the bonds, we call that the transition state. All right. And then from there, after those bonds break, new bonds are going to reform into our products. And so this last point of the collision theory essentials is kind of explaining this, okay? When you get these collisions that are effective and they actually do in fact have enough energy to overcome that activation energy hump, we did say that is at that very top apex, at that very moment, we call that the transitional state. And that transitional state forms something we call the activated complex. Excuse me, let me highlight that. The activated complex, okay? So the activated complex and the transitional state are synonyms. They mean the same thing. Please be comfortable with using both terms, as that's what you're going to hear come up throughout the unit and is what is expected in AP. So at this point, the activated complex can still either fall back left or it can fall right, depending on the situation. Maybe you should just jot this down in your notes, but the definition of activation energy is defined as the amount of energy that's needed to create the activated complex. It must also be achieved for the reaction to even successfully occur. With all this criteria met, you guys, the reaction proceeds. It's moving forward in what we call the forward direction. And actually, it's quite amazing that we even have reactions at all. The last part of this podcast, and then we're going to end here, is a revisit of those Maxwell-Boltzmann distributions that you've heard about in the previous unit. And recall, a Maxwell-Boltzmann distribution is going to show us the distribution of speeds for gases at various temperatures, okay? And you can see that there are two images here in your notes to the right, where we'll talk about really quickly, but hopefully this is not a brand new concept for you and a relatively straightforward. So if you... over here, you can actually, we're going to add a new component to these Maxwell-Boltzmann distributions. You can actually add a point on those diagrams where you can point out where the activation energy is. And what you're going to see on the right-hand side over here is you can see, I'll circle on both charts, where they have designated the activation energy. At that particular energy is when the reactants have been able to successfully create that activated complex or that transitional state for the reaction to proceed. Now, if you increase the temperature, so I'm back over here on the left-hand side, if you increase the temperature, the molecules are going to speed up. And that's actually what the Maxwell-Boltzmann distribution is doing, is it's changing that energy, right? Because energy and temperature are directly related, so synonymous. If the temperature increases, you're increasing the energy. And therefore, you're speeding up the molecules. You're creating more potential for collisions, effective collisions, and correct orientations. And therefore, you would, of course, increase the rate of formation of the products. So only those particles that represent by the area to the right of that activation energy mark are only going to be, are the molecules that are only actually reacting and following through to form the products. So you can see that a great majority initially of reactants don't have enough energy to overcome that boundary to proceed to a reaction. And so again, they just simply kind of bounce apart or bounce away from each other. So the big message here is if you increase the temperature, as you can see here in this second graph, T1 versus T2, where it looks like T2, we are increasing the temperature, okay? That's because more molecules seem to be energetic enough to achieve that activation energy. Thus, you're going to see more molecules reacting and the overall reaction rate will increase, of course. So notice how many more molecules in this second graph are to the right of the activation energy compared to the blue curve, the T1 curve. General rule of thumb is that the reaction rate doubles for each 10 degrees in 10 degrees Celsius increment that you increase the temperature, okay? So rate doubles for every 10 degrees Celsius that you increase. Okay, guys, so this was the introduction of kind of factors that affect chemical reactions, what effective collisions mean, how that relates to activation energy, and all that good stuff. So we're going to go ahead and end here. Thank you so much for watching.